In this next video, we're going to take a look at the lack of fit test. So let's just enter those data values you see there into R. Got some X values and some Y values, just some generic data here. Don't even know what these mean. I'm more interested in the just in the concept here. And let's plot Y versus X. And again, Y versus X, or you can type X comma Y like this, and you'll get a scatter plot of the Y values versus the X values. You can take a look at this plot and see that there definitely seems to be a departure from a linear trend here. It sort of looks like an upside down parabola, right? Sort of this concave downward kind of a trend. So let's build a linear regression model for this and call it, I'll store the output in something called Model 1. And let's do analysis of variance on Model 1. It's just ANOVA of the output there. And you can see the degrees of freedom there, and the sums of squares, and the mean square, and the F values, and this is the test statistic. I'm sorry, this is the p-value for the test on whether or not the slope is equal to 0, okay, for the linear line there. But there's the problem here that I'm seeing by looking at the graph is that I'm concerned that there may be a lack of linear fit problem, right? And I can run that kind of a test, this lack of fit test, if I use first I need to load the ALR3 package. And again, you don't just have to load it, you also have to install it. Okay, so you'll have to install the package and then type library ALR3 to get it in. Okay, and then the function is called pure error ANOVA, with E and error in the first A and ANOVA capitalized like that. Okay, so you can see this is the ANOVA output, including the lack of fit breakdown. You can see that my residual sums of squares is broken down into my lack of fit sum of squares and my pure error sum of squares, and that here's the p-value for that lack of fit test. It's extremely small. It's extremely small, which is very consistent with the picture, right? It certainly looks like it's not a linear, would not be a good linear fit. I could in fact drop a regression line on there just for kicks and see what happens there. Yeah, it's really not a good linear fit at all. Okay. Let's change these response values, however. Change those Y values and redo all of this stuff. Okay, and let's just see what happens. Let's get a new window there and change my Y values, and then make a new plot. Plot X comma Y, and take a look at that. Okay, so on the other hand, so this graph should, if I do a lack of fit test here, I should not see a small p-value, because the data here are trending very linearly. Okay, it's very obvious from the picture. So maybe I'll do regression here. I'll call the output of my linear regression function Model 2, and I'll run analysis of variance on Model 2, and you can see this is the typical ANOVA output. Now if I run the pure error ANOVA, and again, I don't have to load that ALR3 package back in. It's still there. Every time you load a package, it's there for as long as you're running your R session. But if I run this pure error ANOVA, you see that I get all the stuff that I got in my analysis of variance table, but more, right? I still get my my model sum of squares, my residual sum of squares, and the mean square values. Okay, and this is my F test for the slope coefficient, but here where it's indented here, you see this extra stuff. It's where the residual sum of squares is broken down, and it's being partitioned into that lack of fit sum of squares and the pure error sum of squares. And so those are those sums of squares, and then divide those by their individual degrees of freedom, and you get these numbers. And sure enough, here is the p-value for my lack of fit f-test. It's 0.9335, which is very consistent with this point pattern here, indicating that there's really not any evidence at all to conclude that there's any lack of linear fit. Okay, of course I could drop a nice pretty blue line on there just to make it look great, and yeah, so there you go.